Hey students, we're going to cover some covalent bonding notes, and like we did with the ionic bonding notes, you want to make yourself a little Frayer model. So again, you take your paper, you fold in half, you fold in half again, you find the corner with only folds and you tuck that in, and then when you open it up, you've got a diamond in the middle of 4 quadrants, and we're going to use the same 4 quadrants that we used with the ionic bonding notes, so you can do a good compare contrast going on. Okay. All right. So in the triangle, or the diamond in the center, these are our covalent bonding notes. Our covalent bonding notes are going to again have those 4 sections, and then on the back we're going to do special topics. All right. So topic 1, which is the same as last time, pick a quadrant, and that is composition of the bond. And what makes up a covalent bond? Okay. So a covalent bond results from the sharing of electrons in pairs. Okay, I want to stress the pairs part. Sharing electrons in pairs between 2 nuclei. Now, they don't have to share equally. If they do share equally, we call it nonpolar covalent. If they do not share equally, we call it polar covalent. Okay, and I'll get into a little more the polar part of polar covalent. All right, what do you need to be sure you write down? Well, you want to be sure, okay, you want to be sure that you're noting that covalent bonding is a sharing of electrons in pairs. And the pairs part's important. Be sure you put that down. Okay, we have 2 ways we can share. If they share equally, the bond is nonpolar covalent. Unequal sharing is polar covalent. You would want to be sure you've got that there in your notes, okay? We will use electronegativity differences and no negatives. You just big minus small. Electronegativity difference to know which way it is. So in other words, if the electronegativities of the elements are close on the periodic table, there'll be like almost equal sharing. And if they're far away from each other, they will be most likely unequal sharing and polar. Okay, so pause if you need to. Here we go.
Many atoms form covalent bonds. In covalent bonds, electrons are shared by both atoms.
Okay, so you see in this molecule of hydrogen, H2,
by sharing electrons in a covalent
one
bond, each hydrogen
of these electrons came from each hydrogen, because each hydrogen only has one. But they shared them, so they each got 2, which filled their outer valence level. They don't get an octet, they only get 2, and that takes care of them. Now, in water, okay, see how the hydrogens, each sharing 1, do get those outer valence levels, but the oxygen sharing 2, 1 to each hydrogen, also gets its 8. So we get our octets, but it's not by a transfer now, it's by a sharing. And each element gets to count the pair that they are sharing, and so that works out well for both of them. Probably is something very akin to carrying and sharing. So there you go. Okay, topic number 2, the types of elements involved. How am I going to know what kind of predicting ability to know it's a covalent compound from just looking at the elements? Well, okay, I'll remind you last time, ionic was a metal with a non-metal. That was ionic. This is covalent. Okay, covalent is between elements that do not have a large electronegativity difference. In other words, that's between non-metals. So you'd want to write that down. Okay. Now it's possible to share more than 1 pair. So we can share 2 pairs. We would call that a double bond. We can share 3 pairs. We can call that a triple bond. Now, please notice that it's still pairs being shared. 1 pair, 2 electrons is a single bond. 2 pairs, 4 electrons total is a double bond. And 3 pairs, 6 electrons total is a triple bond. So please be sure that you're catching that they're going to share in pairs. As we draw these, we're going to have to be sure we're showing them as pairs because they are pairs, okay? Again, even with a double or triple bond, they do not have to share those equally, okay? Equal is nonpolar and unequal sharing is polar. Right. Okay, so now I want to talk, we're in the same quadrant, so I want to talk about the polarity idea. Nonpolar means equal sharing, no big deal there. The electrons spend the same amount of time on both sides of the molecule. Both atoms get them 50% of the time. Okay. In unequal sharing, there is one element that gets it more of the time than the other. It is the more electronegative element. Okay. We would expect if one element gets the electrons more of the time, the negative electrons more of the time, it is going to be more likely negative on that end. Now, it's not a full out negative charge like with ionic, it is just a little negative warping of the electron cloud. So in my example here, hydrogen chloride, hydrogen's electronegativity 2.1, chlorine's 3. That's a good amount of distance. Okay, sorry, the word was difference there. A good amount of difference. 0.9 is the difference there. That's a large difference. So one of them is going to win the electrons more of the time and be more negative. Which one? Well, chlorine, because it's more electronegative. To show chlorine's more electronegative, we use this little symbol of sigma minus. Okay, and the side that doesn't get the electrons more of the time, we maybe would even say is electropositive, although that's kind of a weird sounding word. It gets a sigma positive. Now you can't just use a positive negative. That's used for ionic. So that Greek letter sigma there in front of the positive and negative, that tells us a partial positive, partial negative. It's not fully positive, it's not fully negative. It's just kind of partially. Because here's the thing, the electrons that chlorine's hogging in this bond, most of the time that bond, that pair is around chlorine, but every once in a while it'll still go around hydrogen. And then it's around chlorine a lot, but then it'll go back to hydrogen. And then that pair is around chlorine a lot, but then it might go back to hydrogen. So chlorine gets it more of the time, and a lot of the time then is more negative, but it's not a full out charge like with ionic. Okay. So be sure you've written down the symbols and HCl as an example of what it means to be polar. You might even make note that this was a 2.1 and this was a 3.0. So the difference of 0.9 is how I knew it was polar. And the bigger number of 3 is how I know chlorine's the partial negative end because it's going to get the negative electrons more of the time. Okay, new quadrant, strength of the bonds. We had this with ionic. So check out what's about to happen here. Ionic was, to review, ionic was very strong. What about covalent? No, not usually very strong, like weak, typically kind of weak bonding. Okay, so you do want to note on your notes that we're looking at weak bonding, not very strong is how I say it, and you can call it weak, okay? So if ionic bonding is really strong, covalent, not strong. How would we, even if they're all covalent and they're all not strong, how would you know which ones are stronger or weaker than the others? We're not going to use lattice energy. Lattice energy was the vocabulary last time. This time we're going to use bond energy. So you want the word bond energy, the vocabulary of that, and you want the definition down in your notes. It is very similar. Lattice energy was the energy to pull apart the crystal. Bond energy is the energy to pull apart the bond because there is no crystal. We might have, now in some of our covalent compounds, organic ones like sugar, you've probably seen crystals of sugar, right? Yeah, because that's a big molecule, all covalently bonded, but it's not still technically a giant positives with negatives. It's just large molecules all kind of like stuck together. So there are some crystals or things that look like crystals that are covalent, but not nearly like, they don't react the same. They don't have the same characteristics as covalent, okay? So covalent bonds tend to be very weak, and we measure that with a bond energy. The lower the bond energy, the weaker; the higher the bond energy, the stronger. Now, while we're on this topic of bond energy, there's something else we can do with bond energy. So I want to mention that here. The bond energy can tell us the length of the bond. I'm probably a very bad father for this, but my son, when I take him out to parks or even the backyard and all that, I don't know why. Like, we could go to a place with all this playground equipment, and what's he do? He wants to find sticks, and he wants to break sticks. And I don't know why. I'm like, why do I even bother taking you to parks if all you're going to do is go stick hunting? Well, okay. So he'll get a stick, and he'll get a big long stick, and he'll grab it. And, you know, he was a child and he was weak and he was like trying to break it. And one time he angled it up on a tree and was going to like karate kick it to break it. And he missed and fell over, and I was laughing, and that probably makes me a bad father. And okay. But you know, probably from experience, if you have a big long stick and you want to break it, not too hard. You take the two ends and you work at it back and forth, and then snap, it breaks, right? Okay. Now, the funny thing, which again may be funny for me, probably not for my son, I then saw him find a large piece of the mulch on the playground that, you know, looked kind of like a stick. So it's about, you know, 3 inches long and pretty thick, and he goes to break that. And he's trying and he's trying, and he can't get hit. He can't break it with his hands. So he, even with like holding it with his hands, he stuck his foot up in between his hands, trying to like, and then he fell over, and I was laughing again. And I probably am a horrible father for laughing at him for doing that. Okay. But experience has told you what bond energy is going to tell you as well. A long bond is easy to break, a low bond energy. And a short bond is hard to break, high bond energy. Okay. So bond energy tells us the strength of the bond. A weak bond is the same as a long bond, and a short bond is the same as a strong bond. Okay. So there's definitely a connection between length and bond energy. And the higher the bond energy number, the stronger the bond, yes, but also that we can infer the shorter the bond. And so there we go. So be sure that you, in your notes, have down that bond length is going to be related to bond energy. And so really, you probably want this whole last sentence. The lower the bond energy, the longer the bond is. And then the reverse is true. The higher the bond energy, the shorter the bond is. Okay. All right, fourth topic. So again, fourth quadrant, properties of the compound. Okay, and again, like last time, you're going to want all of these bullet points, these 5 bullet points put down. Okay, and I'm trying to clarify some things with parentheses, but you pretty much want to put them down. Okay, lower melting points, lower than ionic, lower boiling points. Okay, so you probably have at some point in time tried to melt sugar on your stove, and it's very possible to do. Okay, if it's less energy to melt, it's also less energy to boil, especially compared to ionic bonding. Covalent compounds are always bad conductors. Doesn't matter if you melt them, doesn't matter if you dissolve them, always poor conductors of electricity. So like, spoiler alert, nothing will happen, no matter what you do to it. Okay. Now, we have 2 types of compounds when it comes to covalent. Catch this next one. Polar covalent compounds usually will dissolve in water because water is polar. Non-polar compounds, even though they're covalent, will not dissolve in water because water is polar. Okay, so you see how polar and polar go together, but not non-polar and polar. Okay, it has to be the same for them to dissolve. So we have this saying of like, they mix like oil and water, which actually means they don't mix at all, right? Okay, so polar with polar, non-polar with non-polar is how that would work. Water's polar. So if I'm trying to see, if I want to know, hey, would this dissolve in water? I would need to know if it's a polar covalent compound or a nonpolar covalent compound. Sugar dissolves in water. What do we know now? It is polar because water's polar, and that's the way that dissolves. Oil does not dissolve in water. What do we know now? Oil must be nonpolar, okay? And it is very possible that maybe with my fingers, but they're not nearly as hard as the ionic compounds, okay? They're going to break easier. When they do break, are they going to squish or bend? No, they're still going to shatter, though. It's still going to be brittle. So notice the difference. Not hard, but still brittle. Okay, so there's a similarity and a difference going on there with ionic. So beware of that. Okay, time to flip it to the back for our special topics. On our special topics, I want to talk about intermolecular forces. Okay, covalent compounds are the forces inside molecules holding them together. That's intramolecular forces. Intermolecular forces are, say I have a molecule here in this hand and a molecule in this hand. Are they going to stick together at all? If they do, that's an intermolecular force. This one's bonded covalently, that's an intramolecular force. This one's bonded covalently, that's an intramolecular force. But what if I got them close to each other? Would they stick or would they like not do anything at all? That's an intermolecular force. There are three kinds of intermolecular forces. Okay, so you need to get this down. First type is hydrogen bonding. Okay, you'll want the definition: a hydrogen on one polar molecule to the lone pair of a high electric negative element. It has to be to a nitrogen, oxygen, or fluorine for it to be hydrogen bonding. Okay, so I'll ask, so what do you need for hydrogen bonding? It's going to say, well, obviously hydrogen. Well, yeah, but if I can have hydrogen and not have hydrogen bonding, that hydrogen needs to be able to stick to a nitrogen, oxygen, or fluorine of a second molecule. So that hydrogen must be with a nitrogen, oxygen, or fluorine and then stick to a hydrogen, or sorry, a nitrogen, oxygen, fluorine, which actually means water. Water is like perfect for hydrogen bonding. It's got an oxygen with two hydrogens and can actually do, and two lone pairs, and then it can actually do two hydrogen bonds each, which is actually one of the reasons that water does all the properties that water does. It's polar, and it forms the dome when you put the little dewdrops, you know, on the leaf when it rains, you know, it gets a nice big dome, or maybe you put the drops on a penny and it domed up. Okay, that's hydrogen bonding, holding it all together. Have you ever noticed in a container, water kind of goes up the sides of the container? That's from hydrogen bonding. It's actually like trying to hydrogen bond to the walls of the container and pull itself up. Okay, so hydrogen bonding works if I have a hydrogen and I have a nitrogen, oxygen, or fluorine that hydrogen can stick to. If I only have one or the other, not going to be hydrogen bonding. Okay. The second, oh, I should have cleared it. The second is dipole-dipole. Okay, di meaning two and pole meaning poles. Two poles, molecules with two poles. What do we mean by that? Molecules with positive and negative ends. That is polar molecules. So if I have a bunch of polar molecules, they don't have hydrogen or oxygen necessarily, any of those ingredients, but they're polar anyway. Okay, if I have polar molecules, then they can stick like little magnets with what we call dipole-dipole forces. Okay, so you will want to know dipole-dipole and the definition. Okay, so again, the positive end, see the positive end here? The positive end is going to stick to a negative end, but it'd be repelled by another positive end. And so if I had a bunch of polar molecules that I could manipulate and I put them in a box and I started shaking, I could then open the lid of the box and find that they have all lined up to where the positives are sticking to negatives, the negatives are sticking to positive, holding those molecules together. Okay. Now, again, I'm not talking about the forces inside the molecules. I'm talking about the forces between. Inter means between. The internet is a network between computers. When you go to Google, you know, you go type www.google.com. Okay. It connects your device to a server called Google. And it's a network then between the two, their server and your device. That's the internet, okay? Intermolecular forces are the forces between the molecules. Okay, and there is a third and final type of intermolecular force. Now let's review a moment. Hydrogen bonding needed hydrogen, nitrogen, oxygen, and fluorine. Okay, now it's strong, but that's kind of like limited. Dipole forces only need polar molecules. That's a lot of molecules that could be polar. So it's a much bigger grouping. And then every single molecule out there will do London dispersion forces. London dispersion forces happen when you have random movement of the electrons, creating dipoles momentarily, instantaneous. Instantaneous means it's there for a moment, an instant, and then it's gone again. And then maybe it's back again, but then it's gone again, and then back again. Okay, so follow along with me. What if all of the electrons, for some random reason, because they're moving around randomly, end up on one side of the atom? Well, that side of the atom would then, for a moment, be negative. And so for a moment, it would be attracted to a positive side of an atom. And what if the electrons, the side the electrons aren't on, this positive side, what would it be attracted to? The negative side of another one. So it would line up where, positive and negatives line up. Now, this works for all compounds, even ones that aren't polar, because this is not a dipole. This is not permanent. This is the electrons just happen to randomly be all on one side of the atom. It could happen. Statistically, it probably does happen pretty often, okay? So it's there a moment, but they're still moving, so it's gone the next. And then it's back again, but then it's gone again, okay? So it's strong when it's there, and the more electrons you have, the stronger it is, but it overall is just generally much weaker because it's there one instant and gone the next. That's what we mean by an instantaneous dipole. It's there just for an instant. Not that it appears in an instant. It exists for an instant, okay? All right, so I have a neat video that's going to actually show like some dipole or instantaneous dipoles being shown. So here's random electrons moving around an atom. Oh, did you see them line up for a moment? I got a dipole for an instant, but then it disappeared. But what happens if for an instant I get a dipole on this atom? Do you see how it made this atom also get a dipole for an instant? But how long does it last? It doesn't. It's there an instant, gone again. Dipole, but only for an instant. So we call that London dispersion forces. They're overall really weak because they're there and then gone, and then there and then gone. Strongest of all our intermolecular forces, hydrogen bonding. Somewhere in the middle are dipole forces. And then London dispersion forces, every molecule out there in the world does London dispersion forces, but it's usually very weak. There's rare exceptions where London dispersion forces are strong, usually very weak. Okay. All right. That's the end of our special topics. And so now you have completed notes for covalent, and you should have already had completed notes for ionic. And in the next video, we'll do metallic bonding. So be sure you're keeping all your notes and be able to do a good compare and contrast between it all. I'll see you next.